Hi everyone. I would like to introduce Sun Ho, who is a PhD student at Paris. I met Sun last month at ISFP, where he talked to me about his new tool for verifying Rust programs, and I thought it was pretty cool, and it would probably be of interest to more people at Gala. Yeah, here he is to talk more about it.
Okay, thanks. Hello, everyone, and thanks a lot for the introduction. So yes, I'm going to talk about Aeneas, which is a framework to verify safe Rust programs. Now, Aeneas is actually part of a larger verification toolchain, for which I need to give a bit of context. So there has been quite a few success in program verification in the past 15 years, and this includes verified compilers, microkernels, verified protocols, and cryptographic libraries. But there still remains a big challenge, which is how do we do bigger? And by bigger, I mean, how do we scale in terms of the number of lines of code, or in terms of the complexity of the programs we verify, or also in terms of the breadth of properties we verify, because we often verify things like functional correctness, but we might also want to verify security properties about a program, or also liveness properties. And it's very hard to combine all those properties at once. Now, in order to answer this challenge, we're working on a verification toolchain for which we want to respect three design goals. The first one is that we want to imply the programmer in the spec. So if we want to scale in terms of size of programs and complexity, there is no way the programmer and the proof engineer live in two different worlds. They need to speak to each other and coordinate. So we want the programmer to be implied in the verification process. Also, there are situations in which you want the programmer and the proof engineer to be the same person and to write the code, write the spec, and do the proofs all at once. You also want, in some situations, to have a clean separation of tasks between, on the one hand, the code and the spec, and on the other hand, the proofs. And finally, we want to be able to use a set of tools and techniques for verification. The reason being that, for instance, when you want to verify some properties like functional correctness, you often use a dedicated tool. And when you want to verify another property like security properties, use other tools. And so we need a way of, you need to be able to use all those tools and combine them together somehow. Now, the verification toolchain we're developing today to meet this goal has the following infrastructure. Now, the design choices which led to this infrastructure have been informed by our experience in verifying the Hacklestar and the Average project, which led to the development of more than 100,000 lines of low-level verified C code, which has been developed, which has been deployed in libraries like NSS or Python. So what we want to do is to allow writing Rust code, code in the Rust language, and also write specification about this code also in Rust. And to do so, we provide the HackSpec language, which is a pure subset of Rust. So it's Rust, but with mutable borrows, interior mutability, these sort of things. And then once you've done that, written the code and the spec, you can extract the spec and a model of the code into a theorem prover of your choice. And from there, you can state and prove lemmas, which typically link the code to the specification. And so you get functional correctness proofs, for instance. And the good thing with this architecture is that it allows us to have different people working on the different components. Now, proving theorems about the code by linking it to the spec is only one part of the story. For example, in the case of TLS, it's a good thing that you have, say, an optimized implementation of TLS, and you prove that it refines a pure, easy-to-edit specification. But there is really value if you also prove that the TLS protocol is secure somehow. So we want to give you this possibility by, for instance, extracting the specification to various tools, for example, Squirrel or Tamarind to do security proofs. But maybe you're interested in different properties like liveness properties, and we want to give you the possibility of linking all those tools together. Now, as of today, we have the spec and the code which live in Rust, and then the proofs which live in various different tools. In the future, we want to be able to do at least some proofs, for example, some functional correctness proofs only in Rust by, for instance, annotating your code with precondition, postconditions, loop invariants, and sort of things. In the context of today's talk, I'm going to focus on what is on the right because this is what I'm working on. So the problem is you want to verify safe Rust code by generating a model, an encoding in a theorem prover. And safe Rust enforces a lot of constraints on the code you write due to its type system and the borrow mechanism. And of course, you want to exploit those constraints to make the model as easy, as simple to use and to reason about as possible. So what we do on our side is we take as input a large subset of safe Rust, and we leverage the constraints given by the Rust type system and its borrow mechanism to compile it to a pure functional model, which allows you not to think about memory when you reason about the code. And then we extract this model to various backends. And this is very important for us because you may want to use one backend or a different backend because of your expertise, because of you need some, for example, SMT automation here, or different kind of automation with, say, Isabelle, or you may want to use a specific library which is only available in one of those provers. So we want to give you flexibility in that and don't force you to use a specific backend. Now, in practice, the infrastructure is as follows. So on the left, you have the Rust compiler, and we have developed Caron, which is a driver for the Rust compiler, and which extracts its output. So more precisely, the mir, which is one of the ASTs output by the Rust compiler. So the reason why we have this driver is that the mir is a bit complex, and it's also very technical to retrieve this output. And the Rust compiler, its internals are very unstable. So what Caron does is it takes this mir and it transforms it into a nice, simpler to use AST that we call LLBC. And so it's easy to use. It's meant to be used to analyze the code, and it's stable. And this driver is not specific to the Aeneas project. It's meant to be reusable and as simple to use as cargo. Now, once we've got this LLBC AST, we give it to Aeneas, which is just a compiler, which compiles the code to a pure model, which is then extracted. As of today, we have the following backends, so F-star, Carcol 4, and Lin, and there is an Isabelle backend in the making. Now, in the future, we want to give you the possibility of annotating the code, typically with pre and post conditions. And once we got that, we will be able to generate a pure model plus the statements of the theorems that you need to prove about this model. This way, you won't have to think about how you should state the theorems about the model so that you have the properties you want about the code. We'll be able to directly annotate the code, and then the Aeneas will tell you what theorems you need to prove about the model. So that kind of closes the gap. And once we've got annotations, we can think of having an additional backends, for example, for tools like Boogie, Daphne, Wi-Fi, or Z3 to have more SMT automation and give you the possibility of doing the proofs by staying in Rust and only annotating the Rust code with, of course, precondition, post-conditions, but also assertions, loop invariants, these sort of things, so that you don't have to move. If you don't want to, you don't have to move to a theorem prover. So really, the idea is that there are different styles and different tools, different kind of automations which work for different purposes, and we want to give you a lot of flexibility in this regard. Now, a very important question is, what does the pure model that we generate look like? Because I didn't mention it, but in the subset of Rust that we support, there are things like mutable borrows, for which the translation to a pure model is not obvious. So I'm going to explain you on a very simple example, which is this choose function. So choose here takes as inputs a Boolean and two mutable borrows, and depending on the value of the Boolean, it returns one of the two borrows. Now, the important thing is that there is this alpha lifetime, which links the input borrows to the output borrow. And it tells us that for as long as the output borrow is alive, you must consider that the input borrows are alive, and so they borrow their values. And because mutable borrows give you exclusive access to their values, you don't have access to those values. So in the example below, what it gives us is choose returns you the borrow Z that you can use to do an in-place update. But for as long as you have Z and you use it, you can't touch X and Y. And of course, at some point you can get access back to X and Y, but at this moment you need to end the borrow Z. So the lifetime alpha starts at the function call and ends just before we access X. Now, the beginning of the translation is very simple. So what's on the left is, of course, handwritten, and what's on the right is the result of the translation, which is automatically generated. So the result is very simple. I mean, the beginning is very simple. We initialize X to 0, Y to 1, and at the moment we call choose, we have to compute a value for Z. And we do so by using this pure version of choose, which is basically choose, but we'll remove borrows because those don't make sense in the pure world. Okay, so we just return X or Y. Now, here there's something interesting, which is we use the borrow Z to update X. So this has an effect. But the thing is, for as long as we hold Z, we don't have access to X and Y. So yes, this has an effect, but we don't have to take it into account yet. All we have to say at this moment is we have a borrow, or we could say a pointer Z, which points to some value, which from this moment onwards is equal to 2. So on the right, we say, no, Z is equal to 2. And then we reach the interesting part, which is we get access back to X. We read X to assess that it is equal to 2. And at this moment, the alpha lifetime ends, and we get access back to X and Y. And at this moment, we observe the changes which have been performed on X and Y. So what we do on the right is we say, we simply get new values for X and Y. Now, the question is, what are those new values? Well, it's pretty simple, actually, because as the Boolean is true, we return X. So through Z, we updated X, and Y is left unchanged. So we say that the new value for X is the last value for Z, and Y is left unchanged. But this is the case because the Boolean is true. If it were false, we would have the opposite. So we could write it this way. If true, then we update X, otherwise we update Y. And here we see something which appears, which is that at call sites, we have to use the inputs to compute a pure value for the output. And when we end the lifetime, we have to go the other way around. We have to propagate changes back into the environment. Okay, so back into X and Y. Now we can take this piece of code here and move it into an auxiliary function that we call choose back for backward. And we get the result of the translation. That is, at call side, we use what we call a forward function, which computes the output Z from the inputs. And when we end the lifetime, we use the backward function, which takes the same inputs as the forward function, because we need them for the control flow, for instance, and because we need to remove the old values of X and Y, plus some additional input, which is actually the value which we get back when we end the lifetime alpha. And it returns a pair. So the pair of the new values for the values we loaned to the function. Okay, so this is the whole idea of the translation. Whenever we have a function in Rust, we translate it to one forward function, which is used at call site, and a set of backward functions, one per lifetime, which are used to propagate changes back into the environment to take into account the side effects. And in practice, we have support for quite a large subset of Rust with recursive functions, loops, traits, and other things. Now, just a note before I move on. As of today, this is what we generate. In the future, we intend to change it to this way. We intend to merge the forward and the backward functions so that the forward function returns its output plus the backward function as a continuation. The reason being that there is some duplication between the forward and the backward function that we want to avoid as much as possible. So it would lead to the following. When we call choose, we get Z plus choose back. And then when we end the left, we just give it this additional input, which is the last value of Z. Now, I want to say a few words about the way the translation works, because there are a few interesting things in there. The translation is based on some sort of a symbolic execution. And an important point is that in order to make it work, we need to compute the borrow graph at every execution point. By that, I mean that we need, in every point in the program, to know who borrows what from who. And this way, we know when we end the lifetime, we know which values we consume, we take back, and which other values we give back. Now, in order to do so, we had to introduce LLBC, so the low-level borrow calculus, which has actually some operational semantics for safe Rust. And it has something peculiar, which is that we use lazy semantics for the borrows. So the way to see it is that borrows live as long as they can live. In the case of the choose example, Z is alive for as long as we don't need to access X or Y, because once we access X or Y, we have to end Z. So Z is alive as long as possible. Of course, the difficult point is to correctly abstract function calls, because we don't want to dive into function bodies. We want to treat function calls as opaque. And unless we know the body of choose, we don't know which borrow was returned here. So we had to find a way of correctly abstracting the call to choose. And we did so by introducing a device we call region abstractions, which encode the constraints introduced by function calls. And they encode them just by looking at the signature of the function call, in particular the lifetime annotations. And because of all this, in effect, we actually redo borrow checking. And as a consequence, we don't trust the borrow checker. Okay, so it's time for a small demo to show you the kind of code we generate and how we can use it to prove properties about the original Rust program. So on the left, I have a Rust file, which is handwritten, of course. And on the right, I have the result of applying our compiler on this Rust file. So in this case, it's code generated by Lin, but in whatever the backend you choose, you have more or less the same output. And in all the backends, we have, for example, nice notations for the integral constants, for the model bindings, these sort of things. So I put the choose function on the left because wanted to show you that we get the same thing as on the slides. There's actually a small difference, which is that we have this result type here. The reason being that functions in Rust can panic, so we need to take failures into account. But this put aside is the same. So we have choose and choose back. Here you have another very simple function which just computes x plus 1. It gets translated to this. So there's we introduce, because of desugaring, we introduce an intermediate call for the first addition. And this is a monadic binding because addition can fail if it overflows, for instance. And of course, this is a custom notation we introduced for the constant 1 for the U32 type. So we have machine integers, of course, so bounded integers. Now here we have a simple recursive data type. Of course, we have to guard the recursive occurrences with the box type to introduce an indirection. Otherwise, this doesn't compile. Of course, in the pure world, the box type is the identity because we abstract away memory. So we have just a list. And once we've got this type, we can, for instance, write this list n function, which takes as input a mutable borrow to a list and an index and returns a mutable borrow to the if element of the list. So we just match on the list. If y is equal to 0, we return the current element, otherwise we recurse. So because it uses, and of course, for as long as we hold the return value, we can't access we can't use the list. Now, because there is a mutable borrow, we generate a forward function and a backward function. So the forward function computes the output, and the backward function consumes the updated value and gives you back an updated list. So a value for the list that you gave as input through this mutable borrow. If you look carefully at the source functions, you will see that here we have a function which gives you the if element, and here you have a function which updates the list with this value at the if position. So you have a get and a set. So here you match on the leaf, is I is equal to 0, you return the current element, or you recurse. And here we also match. If I is equal to 0, you replace the current element. Otherwise, you insert the element at the end of the list and you reconstruct the list. Okay, so it's a get and a set. So I think it's pretty natural. Yeah.
Do you have a simple example of how you generate code for a function that mutates one of the references?
Oh, yes. So let's say, for example, instead of T, you have U32 and you increment all the elements you see, something like that, right?
Or even if you just borrow a mutable U32 and you write to it.
Yeah. So the way it does is, okay, the forward function returns nothing, returns unit, and the backward function returns the updated output, the updated number. In this situation, we actually already merged the two. So we only have one function which increments x and returns it. Does that make sense?
Well, I was wondering, where does it get if the updated value is only in the function, how do you know what it is? Or do you, like, you compile the function twice or something?
Something like this, right? So so x plus equal 1, right?
Yeah.
So if you look at it, so what happens? So you increment, so you compute, okay. So in the pure world, you compute the addition, so x plus 1. And then you get to the end of the function, so you return nothing. I mean, unit actually. For the backward function, you don't consume anything because you don't return anything. So, but when you reach the end, you need to, return the updated values to return the result of x plus 1. You
So
see what I mean?
The forward function would not do anything, basically?
Yes, it can only fail. And this is the reason why, in this case, we already merged the two into one. So in the generated code, there will be there will be only one call to the backward function, actually, which just returns x plus 1.
So at a high level, you're really building a lens where the forward function is the getter and the backward function is the setter. And that's why you're changing things to also return a function along with as part of the forward function, because really you're that's the setter function for your lens.
Yes, exactly. Those are lenses. That's a good way of seeing that.
Does that make sense, Gabor?
Yeah, thank you.
So we're doing a similar thing with a heapster tool, representing. So really, what you're doing is you're trying to say a lifetime like lasts for a certain amount of time, and then when it ends, it sort of updates the frame or whatever, however you want to think about it. That's sort of containing it. Right? That's sort of the high level, sort of abstract way you're kind of viewing this, right?
Yeah, more or less. I will be very happy to discuss further the similarities and differences with the
sure,
later on.
Sure.
I read your paper, of course. So, but there are definitely a lot of similarities. Okay, let me continue on this.
Go on. I'm sorry, I didn't mean to derail.
No, don't worry. So, so you have this forward and this backward function. As you can see, there is a bit of duplication between the two functions once again. So the only changes are here and there, basically, which is one of the reasons why we want to merge the two and return this continuation so that we don't have those duplications. Now, in practice, so here we have a recursive function. Of course, we would rather write it with a loop, and we have support for loops. So the way we do it is we generate a recursive function for the body of the loop. And so actually recursive functions, because we need forward function and backward functions. So it leads to the following. We have here the forward function for the loop, so list env1 loop, and then the forward function for list env1 just calls the loop, the function for the loop. So the body of list env1 is essentially the loop here, which is why we just call the function for the loop. In other situations, there may be other things around. But so we have a forward function for the loop, and of course we have a backward function for the loop, which is using the backward function for list env1. Now, if you look carefully, this forward function is the same as the forward function for list env, and it's the same for the backward function. It's actually not very surprising because this function is tail-call recursive. You may also have noticed that I'm using this divergent keyword here. And the reason is that we have to generate a lot of recursive functions because of the recursive functions in Rust and because of the loops. And the problem is that those functions may terminate for non-obvious reasons. And in some situations, they may actually be partial. And usually when you generate a function, a pure function in the theorem prover, the theorem prover requires you to write in such a way that it terminates. For example, in Coq, you need to have syntactic termination. So in the present case, we have syntactic termination because the recursive call is made on the tail of the list, but it's not the case generally speaking. So we need to take that into account. So the way we do it, we deal with it. So it works in Lean, it works in other theorem provers. We made it work in Hall4, for instance. But the way we do it is we use the fact that Lean is a very extensible theorem prover, and so we can have a custom elaboration. So when I write the divergent keyword, actually, we elaborate this. I mean, we implemented something so that this is parsed normally, but this is an encoding by using a custom fixed point operator. And the trick is that the result type has actually three cases: a success, failure for the panics, and diverges. And so the thing is, in the case the function doesn't terminate, we can prove it's equal to diverge. And under the hood, we actually prove at the same time. So we encode this function by using this fixed point, but we prove at the same time a theorem which tells us the encoding we want, the encoding equation we want, which is that list n of t and I is equal to this. And we register it in Lean in such a way that when you use the rewriter or the simplifier to unfold the body of list n, you get what you expect, and you don't even need to be aware of the fact that we have this special encoding. So I will show you how to use that in practice and the fact that we don't actually notice it. So in the case of list n, it's actually not necessary, but for example, if you write this function here, which is the identity if I is positive, termination is not obvious. So this is not a partial function, because if I is negative, it decrements int, you reach the minimum value and then panics. But still, termination is not obvious. So here we do need this divergent keyword and this special encoding. Now we have also support for traits, and something good is that our translation is modular, which is what makes traits possible actually. So we encode traits the obvious manner. So if you declare a trait to U32 here, we encode it as a new structure type to U32, which has one field for the to U32 function. Now, there is something to notice, which is that when you have a trait, actually there is always an implicit type for self, and because things are explicit on the right, we see the self type, which appears here. Now that we've declared this trait, you can implement it, for example, for the type U32, and it leads to this. And you can have a more complex implementation. For example, given T, which implements to U32, you can implement to U32 for option T. So this is what we see here. The important point being that we need an instance of to U32 for T, and you can use it, etc., etc. I mentioned the fact that the translation is modular, and I want to emphasize this. The important point is, for example, if you use a method which has multiple borrows, in the pure translation, all we need to say is we can fully capture the behavior of this function with a forward function with the proper type and a backward function with the proper type. So in a sense, and those are derived by just looking at the signature of the function. So we don't, on the subset we support, the signature of the function gives us all the information we need to actually use this function. We don't need any additional information, and in particular, we don't need user annotations. Okay, so we've seen a few examples of idioms in Rust and how. Yep.
Ask a question. I'm sorry.
Yep.
Before you were talking about the divergent functions. So it sounds like you're essentially using a monad that has it's like a maybe monad essentially, right? Where you have a specific value for divergence. So somewhere, I don't know Lean especially well, but presumably somewhere in there, there's like a non-constructive principle to talk about whether something is divergent or isn't divergent.
Yep.
Is that right?
Yeah. So the fixed point operator, I mean, if I understood your question well, so what do we need to make it work, right? So we need the fixed point operator uses the choice operator. And in the proof of the fixed point, we need the excluding middle.
So this is a little bit harder to do in talk, but Lean maybe has some facilities, and obviously Isabel will do it just fine.
Yeah.
Yeah,
And this
okay.
is also what allowed us to make it work in Hall4.
Okay.
Yep.
Yeah, that makes sense. Thanks.
Other question, maybe? I'm surprised that when you translate get, you don't have to return a new copy of self so that if you were to mutate self, it would be immediately visible to further calls to methods of the same object. Like, do you see what I mean? That I see that when the lifetime A ends, there's going to be a call to get back that's going to give you the mutated self.
Yep.
But what happens when there are multiple, let's say multiple calls to get in sequence, 2 calls to get in sequence? What makes it so that the second call receives a copy of self that is not the original?
Well, the thing is, if you want to do like x dot get and then x dot get, right?
Yeah.
So the problem is when you've done the first call to get, you mutably borrow self. So before you do the second call to get, you need to end this borrow.
Okay, yeah.
Lifetime alpha, and so you introduce the call to the get back function.
Yeah,
you get
I
your
see.
copy of self. Yeah.
Thank you.
Okay. So, okay, so I've shown you what we generate. Now let's see how we can use it to do proofs and the kind of experience we get out of it. So I've got a few proofs here. Here, for instance, I prove a theorem about the mul to add one function. So mul to add one is just x plus 1, okay? So here I just prove the obvious theorem, which is that the result is equal to 2 times x plus 1. Of course, so I do it by, in a tool like Daphne, you would write preconditions and postconditions here because we generate a model in the theorem prover. We have to state and prove a lemma on the side, and we can do it like this. So we state that given some U32 and the precondition that the 2 times x plus 1 is in bounds, it doesn't overflow. No, something important here is arrow x is x seen as an unbounded mathematical integral, okay? So this is machine integral, this is unbounded. So if this is in bounds, and of course the plus operation is overloaded, so this is plus on mathematical integers, and if we look at the body of mul2, this is plus on machine integers, and it returns a result of U32. So provided 2 times x plus 1 is in bounds, then it's mul2 add 1 of x returns some successfully computes a result, and the result is what you want. So it's pretty simple. If we go into the proof, we start with the following goal. Okay, we have x, we have the precondition and the goal. The first step is, of course, to unfold the body of mul2 add 1 by using the rewriter. So we see the body of mul2 add 1 here. And now we really want to, there is a style which works well, which is to write proofs in a horology style, where we say that every function has a preconditions and postconditions, and this is actually how we wrote the theorem here. So we want to do the proofs in this style by, looking at, like, seeing all the function calls here, and whenever there is a function call, we prove the conditions, and then we go one step, we progress by one step. We introduce, for example, the variable for I plus the postcondition of the addition, and then we progress like this in the proof. So for this reason, we implemented this progress tactic, which uses here a theorem, which is the spec for U32, for the addition for U32, and uses it so it attempts to prove the precondition of this theorem, and then it uses it to progress by one step. So it does some bookkeeping. So let me just show you the specification for add. It says that if x plus y seen as mathematical integers, so dot val is the same as the arrow notation. So if x plus y is in bounds, then the addition succeeds and you get the result you want. So I use progress on this theorem, and well, it progresses by one step in the proof. So it updates the goal. Here we see we got rid of the first addition, and we introduced the variable I in the context plus the postcondition of the addition. So just one note, this is the as I is a way of choosing the names I use. Okay, so here I say, please name the variable you introduce as I, but I could name it something else like J. So going back, we have let I equal x plus x, and then I plus 1. Now we have more things in the context, and there remains the I plus 1. Now, of course, you want the lookup to be automatic. So, and Progress is actually able to look at the goal and look up the proper theorem. So we actually don't need to provide the theorem here. There are situations where you need to do so. For example, it can happen that you prove different theorems, in particular with different preconditions on the same functions. But in many situations, you only have one, so you can look it up, and then you can progress in the proof and finish the proof. Now, we can prove a similar theorem that use mul to add 1, and use mul to add 1 just calls mul to add 1, okay? And here the important point is we can reuse this theorem mul to add 1 spec to handle this call to mul to add 1. Now, once again, we want automatic lookup. So for this reason, we introduced a custom attribute, which is pspec for progress spec. So if you annotate a theorem with this attribute, it will save it in a database, and it will actually look at how it is at the theorem statement, I mean, its type. And in this case, it will link, I mean, it will register it as specifying the mul to add 1 function. So now we can remove this so that progress just looks at the goal and looks up this theorem and applies it. So that gives you a way of doing these proofs in a whole logic style. So those are very simple functions. They're not recursive, for instance. We can do proofs about recursive functions. So for example, we might want to specify a property about list env. So the first thing I do here is I introduce this conversion function from my custom list, to the standard lin list. And here I use something specific to lin, which is that it has namespaces. So I can write clist.toList. And if I do so, whenever I have an element of type clist, like the tail of the list here, I can use this dot notation. So instead of writing toList of tail, I can write tail.toList, which is very convenient. So here I can study the forward function for list env. So once again, list env is here. It just returns me the if element of the list. And I can prove, for instance, that if I is in bounds, so this is a precondition, then it successfully evaluates. And the result is the if element of L seen as a standard list. Okay. Now, something important is that here we prove that it evaluates to return of something. So while we do the proof, we actually also prove termination. So we have total correctness. So the proof goes as follows. As before, we again unfold the body. And here there are different sides. Like typically in Coq, the usual way would be to call the induction tactic. There are some situations in which I want to do that. There are other situations in which I want to have a more structured proofs. So here I'm showing you with the more structured proof. So the idea is I might want to, be a bit more explicit about the proof term by writing the match explicitly. This so that I can really match the structure of the initial list env function and have something more readable and eventually more maintainable. So, for example, in the cons case, okay, I get this, then I can simplify, can then do a disjunction on the value of I. If I is equal to 0, it's simple. Otherwise, I can dive into the else branch. Now there's we decrement I by 1, and it doesn't underflow because I is positive because it's a U32, and also it's not equal to 0. And then we get to the recursive call here. And here the good thing is Progress is able to see it's a recursive call, and so it introduces a call to this theorem in the proof term. Now, of course, this theorem will type check only if lin is able to see that it terminates. In the current situation, the theorem has the same shape as the original function, so it syntactically terminates. So we have nothing to do. There are other situations in which it's not the case. For example, here I prove that provided x is positive, then I32 id of x is actually, is the identity function. So here I do the proof in a similar manner, but there is no syntactic termination. So I have to provide an argument towards why it terminates. So the quantity which terminates is x seen as a natural number. So x is positive and it always decrements. And the proof is simple. The important point is we have this possibility of having a termination by clause and a proof that it indeed decreases, and that's very convenient. And once again, the user doesn't have to see that after it is implemented by using the fixed point operator introduced. So that's it for the demo. Going back to the slides. So I've shown you a few idioms and a few examples of proof to give you a glimpse of the proof experience we are trying to have. And I hope this shows you the strength of our approach, which is that we can have a pure functional encoding for a large subset of us, even though it has things like mutable borrows. And by doing that, we give you a way of easily reasoning about these programs written in this subset. Now, of course, we can't support all safe Rust with a pure functional encoding. There are things which hardly fit, if not at all, like, for example, intermutability, concurrency, non-determinism. This won't fit. And there are many, many programs for which use those features and that we want to be able to support on the longer term. So we want to have to expand the expressiveness of our logic to support those more complex idioms. But of course, we also want to preserve the lightweight encoding whenever we can. We want to be able to reason on, to see the code as pure when it doesn't use those features and result with the more complex logic when it does use those features. And finally, we want to find a way of having a unified framework for end-to-end verification. Now, when it comes to verifying very expressive Rust programs, there is an approach which proved to work well, which is to use separation logic. And this was shown by the Rustbelt project, which introduced a very expressive logic to reason about very tricky programs which combine, for instance, unsafety and concurrency. Now, the problem of such a logic is that because it is very expressive, it is also very complex, and so it doesn't scale very well. Now, on our side, Aeneas gives you a pure functional encoding, which is easier to reason about. Of course, it comes at the cost that we have a smaller subset, we have less expressivity. Now, there is something interesting about our functional encoding, which is that there is a natural link we can do between those forward and backward functions and the original Rust code by means of separation logic. So, for instance, in the case of the choose function, we can see it as satisfying this hot report. So it consumes two pointers, which are disjoint in memory, so x and y, and it gives you a new pointer whose value is given by the forward function. And it also gives you a magic one by which you can consume z later on and the moment you end the lifetime. And when you do so, it gives you back access to x and y with values updated values, which are given by the backward function. So there is this natural link between the original Rust code and our model by means of separation logic. So a very obvious way to go is to start from a simple separation logic, like what I'm showing you on the left, and gradually add features, add expressiveness to support features like intermutability or your concurrency, while having constraints, for example, by limiting ourselves to safe code, or maybe mildly unsafe code, something like the kind of code which is today unsafe because the borrow checker is not powerful enough to see that it is safe, but which should morally be considered as safe. And hopefully, by doing that, we should be able to reach a middle ground by which we have something like a simple concurrent separation logic, which gives us more expressiveness than what's on the left, while not being as complex than what's on the right. And of course, one question will be, can we find a way of composing everything? Like, can we find a way of taking theorems on the pure function on the left and by using the logic in the middle and connect the theorems between those two logics? And the default case being that we need to be able in some situations to go from right to left. So a typical case is when you have a function with a safe signature, but an unsafe body, and you use the expressive logic to prove that it satisfies the safe signature. And then you want to see it through the prism of the simpler logic, which only handles safe code. So this is future work. Now, I've given you an overview of Aeneas and the features it supports. So there are quite a few things. We have mutable borrows, we have function returning borrows, we have loops, we have traits. There are things we don't have yet, of course. So we don't have nested borrows in function signatures, and we don't have borrows in entities yet. We have all of the rules we need for that, and the implementation is in progress. It's a bit of a detail. we don't have nested loops yet. It's also in the implementation is also in progress. It's just more generalization of what we already have. And on the longer term, we want to handle more expressive idioms like intermutability and concurrency. Now, put aside what I show on the slides are, of course, many small features that we don't have yet, including many features which just require a few hours or say 1 day of engineering. We're very application driven, so we try to implement the features we need or that people need, and we're very keen on spending some time on any features that some people may need, but we try to be focused so that we can go forward with the applications. In terms of applications, we're currently verifying Kyber, which is a post-quantum key encapsulation mechanism. It's not very big, it's around 1,500 lines of code, but it's very tricky code because it has to be very optimized. And it's a good way for us to test, to assess that our tool actually works, that we have the subset, we support the subset we need, and we have all the tooling and the automation we need. And once we've got that, we intend to move on to the verification of OpenMLS, which is a far more complex program. So it's the reference implementation of the MLS protocol. So MLS is a new protocol for big groups, and the complexity of this protocol comes from the fact that it has to handle the fact that it's very, very hard to add and remove participants and preserve very strong security guarantees while not requiring participants to communicate too much and do too many computations to update their secrets. So the spec is quite complex, and the implementation has a lot of tricky things for optimization purposes. Okay, so I've shown you Aeneas, which is a verification framework, or rather a compiler actually, which given some safe Rust code compares it to a pure model for various backends. I haven't spent much time on the translation itself, but it works by doing some sort of a symbolic execution. And in order to make it work, we compute the borrow graph. We have to compute the borrow graph. And so as a consequence, we don't trust the double checker. And the side product is that we introduce some operational semantics for us. So I've shown you some examples, and there's a lot of work going on to have the subset as big as possible and to actually apply it to verifying real-world examples. So thanks for your attention, and we'll be very happy to take any questions.
Here's a quick question. Do you have some more information somewhere, a paper or something about this low-level borrow calculus? Like
Yes.
a nicer representation for analysis.
So all the rules are described in the long version of the paper we published at ICF in 2022. There misses the rules for the loops. We're currently writing a paper on that. But otherwise, all the details of this low-level borrow calculus are in the paper.
Thank you.
Does the link Jonathan just posted include the forward and backward functions, the lifetime
Okay.
stuff?
So I don't see the link. So maybe Jonathan can actually answer the question.
He just posted. Okay,
Because I
thanks.
don't see the chat.
It has everything. It has the low-level borrow calculus, the rules for the translation, and the appendix with all the extra rules, except like Sean said for loops.
Actually, I wanted to ask you more about, can you give us obviously not, we only have 7 minutes left here, and I don't want to go into detail, but can you give a very high level about how you do the soundness of the translation?
Oh, so we don't have a proof that the translation is sound yet. So.
Oh, okay. All right.
So we're working on that too.
Oh, okay. Interesting.
So the hope.
How did you get it past the reviewers then? I mean, I certainly believe it, and I think it's very useful. And obviously, I'm doing something similar, but it always feels like reviewer 2 is going to be like, "Oh, you haven't proved this out." You know what I mean? How did that?
So yeah. So actually, reviewer 2 was our champion, but I mean, jokes put aside. So we have a lot of precise rules.
Mm-hmm.
I mean, we have a limited set of rules, and it's reasonable to convince yourself by looking at each of the rules that they are valid, they are sound in some sense. And actually, if you look at them carefully, they almost define some sort of a type system. Now, of course, we don't have a proof yet, but we hope, because of the way they're written, I will let you look at the paper, but we hope that we can have a formalization in separation logic to prove that the translation is safe,
yeah.
And this is definitely something in which we're interested, because this is very important, especially to have a more formal link between. So I gave the intuition of what the link should be, but we want to have a more formal link between the result of the translation and the initial Rust code. But this is also future work. For now, we've been focusing on making the translation work on an interesting subset, supporting backends, and proving that the translation is pertinent in the sense that you can actually do verification of that.
Oh yeah,
Use the
sure,
result
sure.
to-
It looks like you guys have done all
Yeah.
the, this picture right here shows all of the different pieces that you guys are connecting to in the backend. It seems very useful. Yeah, okay, we should think about, yeah, because we're working on how do you write that, that sound is proof. So it might be interesting for us to catch up at some point. Okay, all right.
So, and Eddie, to just add to what Sean said, you can hear me all right, right?
Yes.
Yeah, I would say that a way to look at our rules is that they operate in such a simple representation that if you were to try to explain formally what is legal and what is not per the Rust semantics, you would end up with something very close to our rules. They're very declarative. It says a mutable borrow is something that you own or that you lend to someone, and if someone has taken it from you, you don't have it anymore. It's very kind of elemental, very atomic.
Yeah, you're talking about the borrow calculus, right?
Yeah, exactly.
Yeah,
And,
no, I think it's definitely pretty apparent looking at the borrow calculus how it fits with Rust, right? It certainly, I totally agree with you there. But just like, how do we formalize the soundness of the translation to the models, right?
Yeah.
How do we, like you were saying earlier about the connection between the formal connection between Rust and, well, more specifically this, LLVC and its sort of operational semantics or denotype, whatever sort of semantics you want. How do we connect that formally with the sort of translations in the sort of various theorem provers and stuff? I think that's kind of, yeah, that's, I thought you guys had done that already. And so I was like, oh man, that's, okay. Yeah. No, we should definitely talk more about this. Okay, great.
Okay.
we're always happy to have more contributors in the project, Eddie.
Indeed. Is this so that, right. And you did post the most recent draft. Okay, great.
Yeah. And also, let me add one thing on that. If you're interested in a high-level presentation of the rules and how they work and how the translation works, I gave some details in the talk I gave at the Rust form methods in trade group. So that may provide a smooth introduction to the paper.
I think I read it a year ago. So Jonathan came out a year ago. I don't remember exactly how long ago. So I think I read it then. But yes. Anyway, yes. That's useful. I think that's useful context. Thank you. I don't mean to take up all of the time. So sorry if somebody else has any more questions.
Yeah. I don't know if there's no questions from online, it looks like. Yes, we can be done. Thank you.
Okay, thank you.
Yeah, thanks for a great talk.